We'll finish the term up with applications of trig ratios, and in particular look at angles of elevation and depression. Now, usually for this lesson, when I teach it in person, I actually bring in a stick, a long stick. And what I talk about, girls, is that angles of elevation or depression of a point Q from another point P are given by the angle the line makes with the horizontal. So I basically walk around in class with this stick going out horizontally from my line of sight. And when I look up, so for example, if I was in classroom that's 10D and I'm teaching, I would be looking out on the horizontal. And if I saw a bird flying in the sky, from the horizontal, I would look up at the bird, okay, and that would be an angle of elevation. Okay. Conversely, if I was teaching in 10D's classroom and I saw a student going out, you know how you guys aren't allowed out that sort of second entrance, that there's the field and you walk across the field and go out that driveway there. If I saw a student going out there, I'd be looking out at the horizontal and then go, ooh, what's that student going out the wrong gate? How dare she? And I would look down at the student from the horizontal, and that would be looking down at the student on an angle of depression. All right, so there it is in summary, and noting that the angle of depression is the same as the angle of elevation from the different vantage points, okay? And an example of this would be, here is a bird, and here is a cat on the ground. Not a cart, a cat. All right, what's going to happen is the cat looks up at the bird, okay, from the horizontal. That's an angle of elevation. Ooh, there's a bird, okay. At the same time, the bird's up here in the tree minding its own business and goes, oop, I'm looking out at the horizontal and there's a cat down there. That's an angle of depression. And these two angles will be the same. When the cat looks up and the bird looks down, that angle there and there will be exactly the same. So let's just try a couple of examples. Find the height of the flagpole EC. So that's this distance here. All right, so we've got a 34. So this is going to be the opposite, and this is 200 meters. I presume that the 200 refers to that. It's got to refer to that. I just had to restart the program. My computer just crashed. So I presume that this distance here is equal to 200, because if it includes the building itself and there's no reference to how wide the building is, then we need to operate on right angle triangles only. Okay, so if this is 200, that means this here has to also be 200, and we're looking for this distance here. It's x. So that x, mind you, is only going to be the distance from there to there. What we'll do is we'll do the same thing for this right angle triangle, and we'll call that distance y. Okay, so for this one here, we're going to go opposite over adjacent. So tan often is one that is in applied problems. 34 equals the opposite, so x over 200. X equals 200 times the tan of 34. I'm going to hold off working that out just for the moment. So I'm going to get this next one here at the same time. So I'm going to say that that's going to be opposite over adjacent as well. So that's going to be the tan of 64, oh, it's not 64, 62, equals the opposite over the adjacent. That's going to be y equals the tan of 62 multiplied by 200. All right, so flagpole height equals x plus y equals, and now let's go ahead and do it so that we're not rounding upon rounding. So we'll go and say that we've got 200 multiplied by shift 3 for 10, 34, plus 200 multiplied by shift tan of 62. All right, and it's saying that it is 511.0469 dot dot dot. We're in meters in this case. So again, without suggested rounding here, we'll just leave it at that. until it says to 2 decimal places or whatnot. Okay, John wants to measure the height of a tree. Okay, so what you want to do is draw these particular ones. So measure the height of a tree. So here is my tree. He walks exactly 100 meters from the base of the tree. So that's 100 and looks up. So here is John here. So starts at the tree, walks 100 meters and then looks up. Now recall that this is from the horizontal. Okay, so when he looks up from the horizontal. It's also a little bit odd because we don't get John's height. So we're presuming John is literally lying down on the ground and then looks up at an angle of, gee, that's not a very straight line, is it? That's better. Right, and looks up at an angle of 33 degrees. Now, how do I know that his height's not included? Because it doesn't include it in the question itself. Okay, so the angle of elevation, so how tall is the tree? That's going to be x, that's going to be this measurement here. Okay, so we're going to go tan of 33 equals the opposite over the adjacent, x over 100, x equals 100 multiplied by the tan of 33, and that's going to be shift 3, 33 multiplied by 100, 64.9407 ... meters tall. Seems pretty big. 64? No. Yeah, that seems all right. Yeah. All right. Bird sits on top of a lamppost. So here is our lamppost with bird sitting on top. Okay, I just had a student jump on during class there to ask a question. I am recording this during a Year 10 class. So anyway, where was I? A bird sits on top of the lamppost. So there is my bird. Actually, it looks a bit like a person, but anyway, let's just go. It is a bird. Okay, trust me, bird. All right, the angle of depression from the bird to the feet of an observer standing away from the lamppost is 35 degrees. So here is the person, all right, and there's the person's feet. So what would happen is you imagine the bird looking out at the horizontal, and then what the bird does is it goes, ooh, nice shoes, okay? So the angle of depression from the bird to the feet of the observer is 35 degrees. So that's that angle there, okay? Now, many students will mark that angle there, which implies that it's 35 degrees from the person's feet down to looking down the vertical, okay? So that's the marked angle there, very, very important. The distance from the bird to the observer is 25 meters. So the distance from the bird to the observer, so for whatever reason, the bird knows or the person knows that they're 25 meters away. How tall is the lamppost? So that's what we're after there, x. Now there's another way we can write this up, which is actually to think about this like a right angle triangle like that, right? And that's going to be the same as that x there. So let's work out our trig ratio. What we've got is the opposite over the hypotenuse. So we're going to go sine of 35 equals the opposite, which is x over the hypotenuse, which is 25. X equals 25 multiplied by the sine of 35 equals times, remember shift 1 for sine, okay, is 14.339 ... what are we in? Meters, of course. Now, does that seem appropriate? Hypotenuse is 25, it's smaller than that, so that seems like a legit value. Again, if your calc's in the wrong mode, it's going to do something weird. It usually will give you a really weird measurement, yeah, -10. So obviously it can't be -10. So just check the mode of your calculator, make sure. Okay. All right, find the angle of depression from the edge of the top of a 120-meter building. So we're on some sort of skyscraper here. And the angle of depression from the edge of the top of a 120-meter building, so that's how tall that is, which is 240 away from the base of the building. We want the angle of depression. So what's happening here is we imagine this as the horizontal. all right? And we've got a riverbank. Let's just say that the riverbank is over here, 240 meters away from the base of the building is our riverbank, all right? And what we're after is the angle of depression. Try that again. All right, so the way I think about this basically is using pairs of right angle triangles. We've got a 120 meter high. We know that this is 240 long. And what we're after is this angle here, the angle of depression. Remember, it's taken from the horizontal, okay? And the image I want to leave you with is perhaps me walking around with a horizontal or a stick coming out of my eye line going horizontally and then looking either up or down, okay? So that's the horizontal and that's the angle of depression there. So this is the one that we're after. We'll call that one theta. So that means that's 240 and that's 120 because we've got a rectangle here. So I'm just going to go and see what I've got, which is the opposite and the adjacent. So again, with a lot of applied problems, tan is the ratio because they're usually the measurements we have. 120 opposite over 240. Theta equals the tan inverse of 120 over 240. And that will be tan inverse 120 over 240, which is a half, 26, 565, dot, 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 meters in this case. What? No, not meters in this case. Degrees in this case. Right, so that's the angle, which again seems pretty appropriate. Let's see what would happen if my calc was in radians. Yeah, a little bit small angle that. All right, so there's the set work for C. So complete that and have that ready to go for term 4, along with any other exercises that you haven't quite finished just yet.